Okay, hello everyone. I'm happy to present Professor Baruch Spiro from the National History Museum of London. Baruch completed his bachelor, master's and PhD studies at the Department of Geology at the Hebrew University of Jerusalem, master's study in cooperation with the University of Copenhagen on diagenesis of corals in the Gulf of Eilat, PhD on geochemistry and mineralogy of oil shales in Israel, and a postdoc at the Institute of Oil and Organic Geochemistry at the Nuclear Research Center of Germany. And he was the head of the isotope laboratory at the National Environmental Council of United Kingdom. And now Baruch is affiliated with Natural History Museum of London and with our Department of Marine Geosciences at the University of Haifa. Please.
Thank you. I'm supposed to speak in English, understand?
Yes.
Yes. Adventures. I call this lecture or this talk because I want to present different episodes or different studies on sulfur isotopes where we just started and weren't sure about how things will turn up. And so it's not a systematic lecture on sulfur isotopes. It's snapshots on different applications. Sulfur occurs in nature in various forms. Big reservoir is sulfides, some of them economic, big mines of various metal sulfides, or in diagenetic form like this beautiful rhomboids in coal, very typical of early diagenetic pyrite, or sometimes other minerals as well. Here large mines of coal or of sulfides as well, sedimentary hosted sulfides. Of course, they are related to oil, so they come out in the oil itself or as gases. In the environment, sources are due to sulfur in the environment are due to coal combustion, a big environmental problem, or emanations from volcanic sources. See, elemental sulfur is being deposited here, and sulfur gases can travel a long distance. And sediments, gypsum deposits, now aeolian in deserts. Another environmental aspect is acid rain, which destroys forests and also causes damage to buildings in industrialized and non-industrialized areas. So the first show a bit of systematics. That's a simplified sulfur cycle. Main reservoirs are the sulphate and sulfide, with the minerals predominantly iron sulfide or gypsum. And then there are secondary big reservoirs, sedimentary organic sulfur, which is partly derived from living organic matter, polysulfides, elemental sulfides, and elemental sulfur, and all the different interrelations between them. In order to obtain the different components for analysis, there is a relatively complex system of separation of these different species, and they are being improved all the time in order to obtain more precise data for each species. The isotopes of sulfur, there are 4 stable isotopes, 32, 33, 34, 36. The most abundant is 32, 95%. Second is 4.21. And therefore the ratio of this minor, the major, is regarded as an indication for the sulfur isotope systematics. There is a radiogenic 35, which occurs in very small amounts. So, as a delta notation, as for all the stable isotopes, it's against the standard. The ratio in the sample minus ratio in the standard divided by the ratio of standard times 1,000. And expression is in per mil. Here the standard is the VCDT, or Vienna Canyon Diablo Rayleigh. It started with this phase, which was identified in meteorites, and this was a 0. But of course, the amount of this material is scarce, and therefore other materials are used and calibrated against or have this value, and so that's the value itself. As you saw, relatively abundant. This is a newer scheme. Alon Amrani put this nice scheme of the first stages of the processes at low temperature, which are bacterially driven, of reduction of sulfur. It's not his invention, but he made this nice scheme of assimilatory reduction, where the sulfur goes into the living matter, or dissimilatory, where the product is HS or H2S, it then goes into the environment and forms secondary reaction with other species. So one is biosynthesis, and the other is dissimilatory. And you see that difference in fractionation is very large. But also the amount that is going this way is small relative to that way. Because of course there is a limit of the growth of these organisms that can concentrate sulfur. It's a habitat, whereas here it leaves the system, so it's like a factory. So what happens? To make life simpler for me, here is a representation of the dissimilatory sulfate reduction and how it reacts with other phases. So the first stage, there are two stages here: sulfate reduction to elemental sulfur, and then oxidation of the organic matter to produce CO2 and H2S. So it's instead of these very long schemes normally written, this is a condensation of that idea, and here is the overall reaction: sulfate plus organic matter, water produces H2S, CO2, OH. And then things start moving. The reaction, that reaction of reduction can be modeled using the Rayleigh fractionation. And without going too much into the systematics, the important thing is that the ratio at a given time is related to the ratio 34, 32 to start with, the fraction of the sulfate remaining to the power of 1 above over alpha. Alpha is a fractionation minus 1. So in order to understand the system, this would be the first approach to see to what extent this system behaves according to this Rayleigh fractionation. The formula look a bit complex, but it becomes clearer here in this representation of reduction of sulfate in a closed system, starting with seawater. Seawater has a value of around 20 per mil, very close to 20 per mil nowadays, and if it is reduced by sulfate reducing bacteria, have a fractionation that results in a depletion of about 20 per mil. Then when starting with 100% sulfate to 0% sulfate, the fraction of sulfate remaining, one goes from here, this is a product, and therefore the residue becomes enriched in sulfate, in sulfur 34, and therefore the value of the remaining sulfate increases. Is that clear? Seawater is a major reservoir, and it is a starting material for many occurrences of sulfur in the sediments. And therefore, the driver of the system is reduction of sulfur, as you saw before, by bacteria, and the fractionation is about 20 per mil. So at each position here on that path of reaction, the difference between the remaining sulfate and the hydrogen sulfide produced instantaneously is the same. But the product is increase in the remaining sulfate and increase in hydrogen sulfide. And this would be the topic of the first examples. This is already a very old example. Hauptmann-Nielsen, 1969, but it is very educational. They looked at shallow cores in the Baltic Sea and looked at the distribution of sulfur, sulfate, and their isotopes in the pore water. Pore water, very near the surface, is more than 400 milligram sulfur per liter, and it declines very rapidly, 30 centimeters, already less than half. The sulfate is reduced even more. Why is it reduced even more? Because some of this sulfur is now in the form of H2S, and this increases from zero at the surface to more than 70 milligram per liter sulfur at 30 centimeters. And here we can see the isotopes. The isotope increase, and the isotope increase as well. And the sulfur and sulfide together remain more or less the same, which means it is a closed system. There is no loss. So, in relation to this very simple example, now we can look at more at real settings. Solar lake, גם השמש, a sediment of 0.5 meters. This is the concentration, and the concentration decreases very rapidly. Here, the sulfate reduction is very fast. Limfjorden, which is in northern Denmark, 5 meters. It's a very shallow. Also, the rate decreases very fast. But in more open seas, it is slower and slower. Go down in the sediment column, and the change is not as big as, let's say, here. The reduction is very fast or very rapid over that distance. I won't go more into that. It's only an indication how the nature of the sediment on one hand and the depth and the ecosystem of the sulfate reducing bacteria affects the rate of sulfate reduction, which is a driver, as I said, for many reactions of sedimentary or sulfurine sediments. So here is one of the first adventure. I received an email from Harry Elderfield from Cambridge on board the drilling ship. They were working in Juan de Fuca Ridge, and he asked asking whether I would do the oxygen hydrogen isotopes in the pore water. To which I said yes, and asked whether they could sample also the sulfate or water samples. Nobody on board the ship was interested in that, so he took the samples. So the Juan de Fuca Ridge in northeast Pacific Ocean is very interesting in the sense that basement is coming to the surface to the northwest, and then the sediment pile becomes thicker towards the east. But part of the interesting profile is not here. So there are 4 sites, 23, 25, 28, and 26. And the course went through the whole pile of sediments up to the interface. The oxygen hydrogen I will not show, I concentrate on sulfur. And as I say, to make life easier, because the products, there are various products of the sulfate reduction and subsequent reaction, but the first is the loss of sulfate. So here the whole story is about sulfate only. So, like in the Baltic Sea, the first example, that's in meters. Sulfate concentration goes down near 0, and then it goes up again. The isotopes go up. Here there is no material to analyze, so there are no results. But here there is, so there are results, a bit higher. Similar here, goes down, go up again. And isotopes as well. There are 4 balls. Goes down very low, go up. The isotopes. And here, by combining several samples together, there is a value, about 130 per mil, which at the time was the highest value reported in sediments. So something is happening here, and there is a difference between the upper profile and the lower profile, and one can do lots of things with it. Calculate the fractionation or the systematics. You see, it's almost a linear relation between the delta 34 and the 1 over the concentration, the reciprocal of the concentration, 1 and 2, and 1, 2, in the upper part, in the lower part, and here it is very similar. And the other boreholes, again, linear, very good relation between isotopes and reciprocal of concentration, and then it is possible to calculate the respective fractionations for the system, and here they are not very different, similar, etc. And then, therefore, one can do modeling, and so this became a PhD study. And calculate the rates. See, very, very fast on the top and very slow at the bottom. The bottom is, I forgot to mention, the bottom has a higher temperature than the top. It is still within the range that this bacterial sulfate reduction can take place, but this is the reason for the differences in the fractionation. So the different fractionations above and below. Lots of interesting results from relatively few data points on this complex system. But the most striking thing is merely this, the first observation. What does it tell us? Any hint? You see, it's not quite, but there is an element of symmetry. So it means that there is water with high sulfate concentration that flows below the sediment, in between the sediment and the basement. And this was a surprise. It was verified a few years later by identifying emanations of water seeps where the basin, the Heletz-Kokhav basin, goes up again. So in one, there is on the northwest there is replenishment, and then the water comes up in the southeast of that. That was the most beautiful thing from this study, apart from all the systematic work and the calculations and the modeling and so on, and the high values and all the excitement that
what
goes
was
with
the pump? What pumped the water?
Well, it's a question. Is it only the thermal gradient? I have no answer yet, but just the documentation was something. So this was the first sort of, we go into something we don't know. I ask for samples to be collected, nobody else has interest, and it turns up.
Is there a way to follow up on the source because of the ratios?
The source of the water
The sulfur.
here is seawater. There is, it goes in a systematic manner that less sulfate concentration, the higher the isotopes. So it all falls on these fractionations, and therefore the source is seawater.
Coming from the
It's not an additional hydrothermal fluid from a different source, if that's what you meant. So the second second was initiated by a good old friend, Professor Starinsky, who is expert in, or devoted his life to the study of brines. His PhD was on subsurface brines throughout the country, and very interesting, always bring up new questions. And we devised an experiment, or he devised an experiment from which I said, let's do, of evaporation, simple evaporation of seawater through the, as much as one can get, and measure the isotopes. So here are the results, not too many points. The brine goes, and the precipitates. And there was a previous experiment which didn't go that far. It stopped here. So if one changes a bit the cloud and puts them into lines, then there is a line, the brine and the precipitate. These are pairs. So always the precipitate is heavier than the brine. And it is between 1.5 to 2 per mil, something like that. Here, the last points didn't want to obey the same rule. And here, the relation between precipitate and brine is reverse. So we go from gypsum stability to halite, magnesium sulfate, and the complex sulfates, which is from the fraction of sulfate remaining is from 1 to very low, very, very low amount of sulfate remaining. And therefore one can calculate the fractionations for this and that. And that was intriguing. Here. Starting from seawater, because that's what matters. Starting from seawater, here will be the precipitates. In other words, the precipitate doesn't reflect the seawater. And it changes over the range of how much of the initial seawater is actually sampled by the precipitate. In the ocean, in the history of the ocean, there is a change in degree of evaporation of the water, and in certain times the oceans, a lot of the sulfate dissolved in the ocean was precipitated, like the Permo-Triassic. At that time, because the precipitate is heavier than the residual water, the last precipitates is much lighter than the seawater it started from. And this is worldwide. One can, in fact, correlate Permian or Triassic evaporites based on the isotopes. So here we understand. The sulfate precipitated, the isotopic composition changes with the degree of evaporation. One has to verify in which zone it is, and even in the first, the gypsum, there is a 2 per mil difference. So It's another consideration when interpreting sulphate in evaporating minerals. Another system which with sulphate is oil-filled brines. Here it is evaporation. In oil-filled brines, it is organic matter, bacterial activity, reduction. Israel doesn't have much oil, and even the oil fields have only a relatively small portion of oil, the rest is brine. And therefore it is bad for the oil, but one can do interesting work on the brine itself. The oil fields, Heletz-Kokhav, Heletz-Kokhav, in the southwest of the country. So these were sampled, and sampled were also boreholes away from the fields, Gaza and Saad, for comparison. The geological cross-section is quite complex. The Kidod, the oldest here, Iram, limestones, Gvar-Am formation, shales, clays, which is a source rock for the neft, for the petroleum, which is located in the Heletz formation, the sandstone, which is covered by Talmei Yafe and so on. Here, Mavkiim formation are evaporites. We are talking only about sulfur isotopes. The history of that area is complex. Sulfur isotopes, or sulphate. In the diagram of sulphate and chloride, see the seawater here, the boreholes away from the oil fields have high content, and the oil-free brines are the triangles, they should be black, and the ones associated with the oil, the brines associated with the oil is in general lower. So we start here, seawater, non-associated brines. There is a wide range, but in general they are richer in sulfate, and the associated brines are lower. Again, using the scheme of delta 34S against the fraction of sulfate remaining, assuming it was seawater to start with. So seawater would be here, 20 per mil approximately, because we don't know exactly the age of the water, but for that it's not so important. And then Saad, Aza have a higher, and then the samples from Kokhav field and Heletz field fall on these arrays. We sampled several times, and so these three were from the same borehole, but at different times, and these two are from same borehole, different time, and this. So it seems that the system is dynamic. It's not so much a mixing, but it is different degrees of reduction and fraction, and therefore fractionation. Bacterial sulfate reduction and therefore fractionation. The concentration changes with the isotopes. All fall into those arrays. Now if we take it a bit one step further, here is the interpretation. One can express the fraction remaining also as a change of sulfate to chloride. Sulfate is being reduced, chloride is constant. And therefore, the line either this way or first there is fractionation, perhaps evaporation too, and then this aspect, this pathway, like this or like that, to form the brines now located in the non-associated brines of Aza or Saal, and then these fall on distinct lines. Each of these two has a slightly different story, but they follow a very similar fractionation. This is calculated 101 alpha, so this is between 101 and 102, both of them, whereas this is much steeper. Few data, something to think. Now it's a different story. No more sulfate reduction. We don't know the system. We want to find out what is the nature of sulfate in rainwater in Israel. And this was work done with Baruch Spiro. So the rain was collected throughout the country, from the north, on the coastal plain, Jerusalem, Negev, and the chemical analysis shows good relation between sodium and chloride, magnesium, all fall nicely on the expected line. Seawater concentration. This is the seawater line, but potassium has some anomalies. Sulfate has some anomalies. This is seawater. There is excess sulfur, excess sulfur, and also excess calcium. Calcium is not surprising. There's so much calcareous sediments in the country, but sulfate, and that's the whole story. Again, using the same principles. Chloride to sulfate ratio, and the fraction of sulfate remaining from zero. Seawater is here. 20 ml, chloride to sulfate ratio here. The present study are the black ones. But there are other studies as well. Here are the various possible sources. Number one, sedimentary rocks in general, soil in general. 4 is coal, wide range. oil, volcanic, biogenic compounds like DMS, dimethyl sulfide from the ocean, etc. So, big range, which would be independent of that. Big range on possible sources, independent of chloride over sulfate. So in other words, regarding those sources, there is no need for this to be a straight line. It could be a cloud, but there is a straight line. Why is there a straight line? A mixing line. And the mixing line ending at zero. Zero is this meteorite. Looks like arbitrary almost. And as I say, no, it's not the only study. And here is Ramon. This is Mitzpe Ramon. And the gypsum in the Martesh is of Triassic age, and it is 10 per mil. So the local source even can affect the rainwater that comes down. But overall, it's not enough one determination to make a story, but it was curious to see the reflection. So, what does it mean? I was puzzled. And then I got a call from Fang Zhizhao, a Chinese postdoc at Rosamsted. Rosamsted is a very interesting place. It's located about 40 kilometers, 50 kilometers north of London, and it is now an agricultural research station. But it was founded by the owner of the farm, who in 1845 set out a large project of testing fertilizers. He wanted to see what fertilizer is appropriate for various crops. So there are all these plots of different crops, mainly herbal, and over the years, lots of experiments were carried out there. Now it is a BBSRC or a research station, a government. But there is one area that was never cultivated and never got any fertilizer. But every year the grass was cut, and every 5 years a sample of soil was taken, starting 1845. It's called a park grass experiment. And this is this area here. So in a little rusty shed with even rustier lock, there was this treasure of nice jars. Every year the cut grass, every 5 years the soil. And Fangji was interested in the relation between in the soil, how much of the the rainwater affects the soil. I was interested in the grass, so we did the work together. And this is what the result is. The whole truth in one page. These are the UK sulfur emissions starting 1860. This is calculated from the coal board that controlled all the coal operations in Britain since it was privatized a few years ago, or it was disbanded. So there is a record of sulfur emissions calculated from coal combustion for this period. It goes up, a maximum at about 1970, and then goes down because of new regulations. Whether the sulfur comes from the soil into the plant, or the plants have any effect on that, this is a phosphorus. No change, not much change in phosphorus. So the nutrient taken from the soil don't change much. It's depleted. There was no fertilizer, but the depletion is small. The sulfur content in the plants follows approximately the sulfur emitted from the coal. Goes up, goes down. The isotopes go down and go up again at the same time. So more coal combusted, more sulfur in the atmosphere, more sulfur in the atmosphere, more sulfur in the plants. And the plants reflect what happens in the atmosphere. So the story of the atmospheric load of sulfur for this period, 150 years, is recorded in those jars that were collected each year. If we put it on that, SO2 emissions, the herbage concentration, the isotopes. And the maximum emission coincide with this zero value. This, the highest emissions of coal here, coincide with this near zero values of atmospheric sulfur. And this is the answer why here the mixing line this mixing line is a long range with very little chloride. Yes, it's very little chloride. So it's a sulphate, rainwater which doesn't contain chloride, it's rich in sulphate. Is a long range transport of contamination from which we have to assume, therefore, is the coal combustion is the main component. This treasure was also a source of material because from all plots there were other aspects. What I wanted to say is that this possibility of doing a 150 years period helped us understand CO2, the carbon variation, CO2 variation of carbon in the atmosphere, how it is taken in plants, and how it is, what the record actually showed. And it was so successful that Frank Jijau could build a stable isotope laboratory at Rosamstedt and then now he's professor at Nanjing University. So it was really a exciting time being able to tap into such a treasure. So that's Rosenstedt, and this was my last part of the adventure.
Thank you very much, Baruch. Any questions, please? Okay, no questions. Okay, no questions. Thank you very much.